So one of the most rewarding things or personally gratifying things is getting invited and also to have an opportunity to discuss with great minds in round tables and also panel discussions, and also just meet the quantum enthusiasts and people who are also in this case more focused on the climate and sustainability topics, which are most important, I think, for each one of us. So thank you, Maëva, for inviting me again. And then hopefully we'll have a great 45 minutes to 1 hour session. The way we have planned this session would be that I'll start with the introductions and I'll invite the panelists to the round table. Then I'll also give you what we will cover as a topic. But in case if you have any specific topics that you would like to discuss or questions, please throw them on the chat window. I'll also follow them and I'll uh, put them up at the right time. So without further ado, let me invite the people who make the round table so great. So the first one is Miss Rima Kasia Oueid, who is a commercialization executive at US Department of Energy. Rima is a commercialization executive right now, but has a rich history, both combining her experience in finance, strategy, and also energy policy expertise to identify markets, public-private partnerships, and also working with a diverse array of stakeholders. So I really liked the background where I was reading about Rima and preparing for this session is how Rima has been involved in commercializing innovative technologies and tap diverse capital to deliver holistic energy solutions. So very diverse background, both from private and also in the public space. Welcome, Rima, to this panel. And then the next one would be Daniel Frank. So now this is a perfect combination where you have someone from the industry, and the second one when you combine them with someone who has brings in the money. So this is Daniel. So if you don't see enough investments in the right direction into these areas, then we have a person who represents the entire voice of the VC area. So Daniel's background, Daniel is a principal at M Ventures, a strategic corporate venture capital fund of Merck. Merck, which is the leading science and technology company with over 57,000 employees. Daniel is responsible for technology investments from M Ventures Science and Technology Fund. He obtained his bachelor's and master's degree in chemistry at RWTH University before moving to MIT for his PhD studies. And he has worked on various different functions and research, but then mainly on developing the functional materials for display technologies and advanced biomedical imaging applications. Welcome, Daniel, to this roundtable. And last but not least, Dr. Mansour Taghavi Azar Sharabiani. Fantastic background coming in from the world of teaching, a lecturer at Imperial College London. The thing that stuck for me is leading a lecturer, leading machine learning specialization for master's programs. So everything that we were discussing, even in the last 15 minutes that I joined the previous session on metrics and how the measurements, I think Mansour will play a key role now and also in the future through him and through his students on solving the problem of metrics and how we measure, how we optimize, and how we deliver on the promise from quantum as well as from supercomputers and HPCs in general. Mansour has been actively engaged in solving real-world industry problems in areas such as developing deep learning algorithms for the analysis of synthetic aperture radar imagery, and a more recent example in his research on transforming non-linear programming problems into QOBOs, quadratic unconstrained binary optimization, and many, many more. The list just goes on. But here I'd like to welcome Dr. Mansour also to this roundtable. Welcome, everyone, and let's get started. All right, so the session itself is being planned in a phase where we set the scene. So we'll ask some generic questions around computing, around quantum, and the climate crisis ahead of us. Then we look at the role which is there in the computing industry, the role of HPC centers, currently the role of the industry, and then we will go forward to say what should we do in terms of the actions and how do we conclude with international focus, collaboration, and research. So this is how the questions are phrased, but then we will follow the flow and also the momentum within the roundtable. So the first question, I'll open it up, and anyone who wants to take a shot at this point can take a shot. But then in some of the questions, I'll also direct it to the specific panelists here. So the first one is the 2021 report. If you look at it from United Nations, Climates Conference held in October 2021. Build it that we are at a point, at a pivotal point in the world where this is our last best chance to limit global temperature rising beyond 1.5 degrees, which could turn into catastrophic implications. So here I'm quoting exactly what was said as a warning. There is an increased urgency to solve these problems. So where are we with technologies, both in computing, the current computing technologies, and also in a technology like quantum computing to solve these problems? So what is the current state? With the silence, maybe I'll put the question to Rima first, and then I'll take it from there. So Rima.
Sure. So I think in terms of quantum computing, to be able to do things that will allow us to address climate change, I don't think the quantum computers are there yet in terms of, well, I take that back. There's obviously certain things we want quantum computers to do that we aren't there yet on, but there are things that we can do along the way that help. If you look at quantum technologies more generally. So earlier in the discussion, we heard someone talk about it was Cold Quanta talking about quantum sensors and how that can be utilized to help, with retrieving better, more precise imagery so that we can identify methane leaks and other greenhouse type gas emissions. And I do think that that is a very valuable and useful tool that will help us, combat climate change because we'll be able to hold emitters accountable, and I think that that puts people on notice, and it could help incentivize better behavior, especially if we, pair it with other ways of incentivizing that good behavior. Talking about carrots and sticks, but at the same time, I do think that classical computing can also be helpful, but we may have to approach it in a different way. So a lot of the imagery, so just kind of honing in on this idea of how do we, survey what's going on Earth in order to achieve proper behavior to reduce emissions. We could do things better classically, but that would also mean, potentially deploying some of the computers that run those algorithms maybe in outer space, right? Putting data centers in space, which is there are companies that are doing this and exploring this. And so that could help us achieve better information and data because you wouldn't lose all that data coming down to Earth. And therefore could be processed with fewer errors and provide more rich information. And that's using just classical computing. And then when you add quantum on top of that, that just takes it to another level. You know, I think that we're headed in the right direction. There are things that we can do now, and then there are going to be things that we're going to do better later. So all is not
Okay.
lost.
Thank you. That's a very promising start to say that all is not lost. So we do have hope. But then that was also a question which is loaded, and I'll tell you why. Um, I sell quantum computers as part of my everyday job, and although there is a hype and there's a lot of media attention, you see quantum everywhere. But then, Rima, if I take the summary from what you just said, the gist, it is all about computing and computational power. It doesn't matter. Quantum is one way to approach it. Yes, it's more powerful, gives you the exponential tool, but then it's about solving problems. And what I realize, at least in my everyday job, is we are still few years away before quantum can start delivering on the promise. Yes, there is needed attention because you need to prepare now a quantum readiness to be able to solve problems of the future. But it's also like a relay marathon. So supercomputing centers will continue and it needs to pass on the baton at some point in time to quantum. But then I don't think we have reached that point where the baton can be passed yet. But readiness is important, momentum and preparation is important. But somehow I don't think there is quantum that can answer the question right now. And that is where I think supercomputers play a role. And maybe one more small piece. I've been attending Supercomputing Asia event in Singapore currently, and I'm here was over the last 2 days. And the kind of progress with the exascale that's being done, I think there are many powerful tools that are also coming up till we reach that point of quantum advantage. Maybe let me put the question to Daniel, who would be receiving several of these proposals and pitches on solving these problems. So, Daniel, what are the tools in our armory right now that you receive, which companies, both established corporates as well as startups, are working on to address this climate crisis? So, what are the technology, especially from the computational side, that people are pitching to you and then presenting to you?
I mean, it's a very interesting question. I think if you actually take everything computing right outside of quantum, I think we see a lot of crazy stuff right now, and crazy in a good way. And right, you can see if you look at Moore's law, right, it's tapering off. You see a lot of people investing in kind of interconnect technologies, right, in data centers to work on like data flow bottlenecks and so on. But at the same time, we see a lot of really emerging compute architectures, right? So that's things like photonic-based computing, right? Not even photonic quantum computing, just regular classic computing, right, with photons. You see all kinds of analog architectures emerging, right? So kind of like resistive RAM-based architectures for memory compute. We see things like hyperdimensional computing, right? So really take any word and then throw it in front of computing is probably a subgenre of things that's raising money right now. And I think quantum is probably one of the most prominent ones, right? Because there's lots of companies, it's a clear story, I think. Lots of companies that have raised good money as well, and lots of funding. I think that has attracted kind of the broader VC community. In terms of, I guess, of time to market, right? And what are they really solving problems that are short-term tractable? I don't think the amount of money that has gone into quantum matches that at the moment. All right. I mean, there's lots of money gone into it. There's other kind of emerging compute architectures, I would say, that are, at least for some other problems, also equally promising, that have not received that amount of funding. But for quantum, at least, I think it's likely going to be more somewhat of a step function, right? At some point where all of a sudden the increase in computational power is going to outweigh that and kind of switch that flip around between all the VC money that has gone into quantum computing and then all of a sudden the really, really important problems that we can solve with it.
Thank you. So you again, even in the first 5-7 minutes, we have used a lot of computation as a word, and we are talking about it. But then in the world where we live in, at least majority of us on the call, we would assume that there is computation power available all around. So maybe I'll pose this question to Mansour in a way. What are the mathematical or what are the problems around us that we are not able to solve right now with computational power that we have? Like if you give an example of say use cases or some of the data that is around us that's available, which we have not maximized to solve a problem. So what would that be?
Thank you for inviting me. I start from my case because I was biogas production is one of the industries that promised to contribute, I think, to 12% reduction in gas emissions. So it was one of the most relevant industries in the field. So I have a long experience in business optimization in other sectors, but I was very pleased that I get involved in this project because this was, I thought I can contribute even a small step in the tackling climate change. The problem with this biogas optimization was that the space is very, the decision space is very highly dimensional and is very large. And then using classical computing power is not the answer, even using clusters, supercomputers. And at the same time, I was so I was thinking that I'm trying to simplify the problem, approximate, simplify, use this assumption, that assumption, simplify problem more and more. Then, of course, the more you add assumptions and you simplify further, then you are less accurate in like solving your problem. And therefore, I was thinking if there is a way that I don't have to, or at least minimize the level of simplification. So therefore I was looking for alternatives for classical computing. And then I realized there are many different frameworks of quantum computing. And of course, there are other like quantum inspired approaches as well. So I started to investigate about quantum computing application, and because I was looking for a low-hanging fruits, I was not going to revolutionize quantum computing or try to go the most difficult way. So I was thinking maybe quantum annealing is the first step to go for, and then. But the problem with quantum annealing is that it doesn't solve continuous problem. So that's why I came up with this. In the paper you see is QNLP, but now because we revised substantially and we have submitted the revision to one of the highly credible journals, and we are waiting for the results of our revision. So we changed the title or the algorithm name to QANCO, which is quantum annealing continuous optimization. And then there are, of course, 4 steps. Let's say this quadratic approximation, then discretization, then binary representation, and then solving, which you can use any Ising solvers, such as D-wave annealers. We tried this, but again, it refers. I also maybe somehow I'm referring to about performance metrics, and you mentioned one of the advantages of the research we did in our paper is that we could, without adding additional constraints, we could calculate theoretical minimum. So then, without having to run the computational power. Therefore, we could see how quantum computing is accurately goes, or how close goes to the true minimum and with what speed. Of course, there are some problems with measuring the speed, or maybe in the later I say, but for example, because we have overhead over the internet, and yes, that others. Yeah, so I started with this with algorithm, and I think this algorithm opens up not just for biogas optimization problem, but for any continuous optimization problem, which can be solved with annealers. Of course, at the same time, we are looking for quantum gates approach frameworks, but they are the next steps. But yeah, so at least the first real experience that I had is tackling biogas optimization problem using quantum annealing. Yeah.
Thank you. That's again, now when we are talking about solving a problem, we are depending on technology. Now, in all your answers, we have been trying to build on that and look at how technology will solve the problem. But the pessimists in the room would say, has that not created the problem in the first place? Because we have always looked at technology and we are always advanced in a way, like all the data centers and so on that we have is there exists and it emits so much whatever pollution and the climate crisis because we have the tools like smartphones and others which generate so much data with IoT and so on. So is technology a solution? So the question is technology really a solution, be it quantum computing or advances in supercomputing, a solution to address this problem? So to set the scene, are you seeing anything from industries, like specific industries that you feel that yes, they are speaking of the right problem, or there is hope that computing solutions will solve the problem? So do you have any specific examples from the industries that you're working with? Maybe Daniel, I'll put you on the spot and say, do you see anything or hear anything from industries at all?
Yeah, happy to. Right, so I mean, you said already said, right, we're a venture fund, but our corporate is Merck KGaA, Darmstadt, Germany, right? And we have three main businesses. We have healthcare, life sciences, and electronics, right? And all these three businesses, especially over the last 5 to 10 years, R&D is to a very big degree now driven by computational research, right? And that could be things like quantum chemistry, right? And that could be quantum chemistry for
All right. Well, Daniel is coming.
okay, guys.
Yeah.
Oh, can you guys
You're
still hear
back,
me?
Daniel. So continue. Yes, we hear you. We lost about 5 seconds, but you're back now.
Okay, good. Yeah, so essentially, right, so it's very computationally driven already. But what we notice, especially for let's say these emerging technologies, right, whether it's quantum, whether it's neuromorphic, whether it's photonic computing, it's usually a tech push, right, where people in the industry or in academia come up with kind of a new compute platform. And then at some point they show up and say like, hey, we have this awesome thing here. It can do this, right? It can do, I don't know, it can run this kind of algorithm. Tell us what you want to have. And that's definitely a divide. And especially in quantum, I think we've seen this disproportionately so, right? There are a lot of companies approach us, say like, hey, we're building this thing, we're early. Do you want to be our customer, right? For us, we saw this, and we saw it also in industry peers, right? We obviously have a lot of other corporate venture funds, for example, we work with, and we know their R&D teams. And so what we did to kind of counteract that for quantum specifically is in Germany, we started this QTech organization, which you may have heard of. It's a consortium of a bunch of larger German companies. So Siemens is in it, SAP, BASF, BMW, Volkswagen, Boehringer Ingelheim, us. So it's a pretty big consortium essentially of people. Bosch, Infineon, I'm probably still forgetting some. But the idea of this consortium is that we wanted to have few people that understand what quantum can do, right, from a basic understanding, but also understand what the industry is interested in. And now with the goal to generate use cases, right? So you kind of have a library of, I don't know, a couple of different work streams, right? Maybe some in materials, maybe some in finance, maybe some in general optimization. And really build use cases to put out there, right, for everyone to use, for everyone to see, letting people know this is actually valuable for the industry. Because I think right now there's still a pretty decent gap between what people are building and what people want. So yeah.
Thank you. So maybe, Rima, if I can just build on the same one from the public policy side and also from the energy industry where you have been closely involved in the recent times. So do you see the public policy and also conversations in terms of the government policies across the world, but mainly also from the US, enabling that? So do you see like there is a government push either through increased taxation or rebates or some kind of saving to ensure that industry goes towards solving this problem using computation?
So I think the general sense in the United States right now is this pressure to reduce greenhouse gas emissions, and this is coming, from the top, right? And there are various types of programs that have been announced, and infrastructure programs that have been announced to help incentivize companies to want to drive towards those, to be viewed and perceived as cleaner and sustainable. And in particular in the energy industry, one thing that I am seeing is this interest in figuring out how to use more clean energy, right? And that's going to significantly contribute to reducing concerns related to climate change. So, for example, there is this industry consortium called the Quantum Economic Development Consortium that was stood up. It was federally mandated, and it is a consortium with industry. And we've been collaborating with them. We are a member, the U.S. Department of Energy, and they hosted a workshop last week where we brought in, where the utility industry was involved, the energy industry was involved, to think about how to leverage quantum in particular to benefit the energy industry. And some of the use cases that were identified, the ones that really stood out was energy optimization. And what could you optimize for? Well, to leverage more renewables, right? That is an optimization problem. And especially when you're thinking about renewables at the distribution level. So we're talking about now leveraging energy from that was traditionally, on the transmission side, but now we're talking about energy on the distribution side, and how does that all interplay together, and how does that get optimized? Well, this is something that quantum computing could be helpful, and not just the fault tolerant gate-based quantum computers, but we could use near-term applications like quantum annealers. So there's interest, and there's utilities that are working with us on this, and I see opportunity there, and I think the urgency to reduce climate emissions is helping maybe even advance adoption of quantum technologies. It's interrelated.
Thank you. So maybe there's one housekeeping message that has come up, that there is some volume disturbance when speakers are speaking. So maybe either it's getting low or there is variance. So if the panelist is not answering, then if we can mute our mics, then maybe mute and unmute, that will be better. All right, so maybe I'll put the next question to Mansour, and then this is more in terms of, you mentioned your algorithm that you are now looking at, and it will be at some point be approved and then it accepted and it will be published. But then in that process, I'm assuming you also worked, as you said, with the annealing, quantum annealing. But what is the role of a quantum hardware versus a quantum algorithm to solve these problems? So how do you see the match? Is it hardware agnostic, or is there a role that each of these plays significantly, and what is the difference? So for our audience, if you can explain how does it?
Yes. Actually, first of all, the relationship between hardware and software, to my opinion, is complementary and symbiotic. Take example of, assembly language when the computers started to be built. As the invention of C language was a great success, that people start to increasing the applications, and as the applications and different domains started to take up, and then as the software start increasing, the demand for hardware also is increasing. So they are helping each other, and there is a bigger market for computing. The same way, of course, I don't know if I'm wrong or right, but probably we can say that quantum computing is not in mature state, it's in early states. And there are problems with the number of, in hardware perspective, they want to increase the number of qubits, the connectivity, for example, sparseness in annealing, some of the annealing hardwares. Then we want to reduce noise and decoherence. These are the problems should be overcome. But now there are, like we can see, domain-specific languages are coming up. For instance, example of C. So we can, like, let's say similar to C#, like we have now Q# made by Microsoft, or there are IBM has their own domain-specific languages, and then also the availability and accessibility. For instance, we can access some of the hardwares, like some of the computer hardwares via Amazon brackets, for example, is like accessible. So the more it becomes accessible, then we have more application, more use, new ideas are coming, and then the more problems we solve, the more demand increases. So then there's more investment for hardware, and they overcome the more. For example, if you had a much more number of qubits now, I would have been able to solve much bigger optimization problem. But I just wanted to say that the data I'm using is belong to Nature Energy, which is the largest biogas producer in Europe and one of the largest biogas producers in the world. And then it's clear that with few percentage increasing efficiency, we can save a large amount of, we can reduce a large amount of emission through optimization. So this, then there are also, I mean, about, I mentioned IBM, and then there are Rigetti Quill language, I think Rigetti or Rigetti, I don't know how to pronounce correctly, but yes. There are some, that's kind of inventions are coming, but as I said, they are symbiotic. And also one thing, sometimes we are, our failure in using the technology in quantum computing can help us. For example, one of the, probably one of the efforts was to use electrons trapped in the synthetic diamonds, which are very sensitive to magnetic fields. So I know that some people have thought to use this side effect or this problem to create new generations of NMR machines, probably in a smaller scale or more accurate. I'm not expert in that field, but yes, all these interactions create either directly through quantum computing or indirectly leading to creation of new inventions. Yeah.
Fantastic. So there are a few points which I took in, like one where you mentioned that the number of qubits is not there, so it's still in the early stage, mostly quantum computing. Yes, that you can run some of the algorithms maybe, but it has not proven to deliver quantum advantage right now. That is, it can outperform a supercomputer. So that's a fair observation, and also from my workplace, I do see it. But there's an alternate approach which we are also trying, and which some of the industry is starting to pick up, is on digital analog approach of quantum computing. So it's where you don't no longer depend only on the number of qubits, but you can bring it through a digital analog approach where it's a hybrid way, where the chip can be designed for a specific problem. We have a team which is working on, but it is still in early stages, like the industry itself. But the potential from the research and from the simulators show that then the number of qubits that you need does not need thousands of them, but maybe with tens of qubits, still you can solve a problem. So it will be interesting to see. Just I thought I'll say that there is an alternate approach where the number of qubits challenge is being addressed. At least one of the ways we are trying it. And maybe also to add, you also raised the NMR one. So coincidentally, we have worked on only one problem at this point, which we have published, and that is based on this NMR image resonance. So I can also share the paper with you. So, and
also one thing I
maybe
wanted to add, with a fixed number of qubits, maybe improving connectivity and can be another solutions to like when we have a dense when this sparseness of the connectivity is reduce the amount we can use the qubits, as you mentioned, then it's another way to get around this. Yeah, and also one thing I wanted to say in previous section, I mentioned, I knew that I'm not going to solve problem with quantum computing right now, but developing these algorithms, they have a learning curve. Even if the computing power was there, if we had like much bigger qubits, we wouldn't necessarily be able to just use right away, because at this stage, actually, it's a bit like also we need to know a bit more about quantum computing itself, like early days of computing, as I said, like assembly languages. You had to know more, you had to be more involved in quantum. It was not like nowadays you just program high level and you don't care what happens behind the scene. So these are some other forms of problems that we see, and the more we end up with higher languages, higher level languages, then we will have much more applications. Yeah.
Thank you. Now that's a fair one. So with the languages and hardware and setting the scene, now let's switch to the industries. And here I would definitely want, Rima, your opinion more in terms of quantum adoption. Quantum is like any other new technology which will suddenly, at some point, once the first company cracks it, every industry would want to adopt it. So there will be a race that will come up at some point in time where there'll be euphoria and the demand will suddenly increase. So the question is, what are industries doing today, or what should an industry start doing today? Because most of the participants are also from the industry background where they're considering, should we enter into quantum, or how should we enter, or how should we start with quantum? So what have you seen from your experience in different transitions and different technology disruptions? What should the industry do today to start or be prepared for quantum? You are on mute also, maybe.
Thank you for that. No, it's a good question, and it's interesting when you look at history and who the innovative disruptors have been. They oftentimes have not been the legacy companies. They've been the new kid on the block, the newcomers that come in and just literally turn an industry upside down overnight. And quantum could happen. That could be another one of those industry disruptors, and the industries that it can disrupt are many-fold, depending on whether we achieve the a fault-tolerant quantum computer. But finance is obviously looking into this because they have to. I mean, it's just it's cutthroat, right, to compete in the financial markets, and they can't afford to be behind. And obviously the pharmaceutical industry is very heavily looking into this as well. And now we've got the energy industry, I think, coming up to speed, right? And because they see some near-term applications. But to Mansour's point, folks need to start looking at this sooner rather than later, because there's going to be a learning curve. And as he pointed out, even if we had what we needed today, would we know what to do with it? Would we know how to build the algorithms and ask the right questions to get the right outcomes? And can we test them empirically or benchmark them against something? So building that expertise now, playing with these things now, makes a lot of sense, and we're seeing that happening in the finance industry, and pharmaceuticals, and now in the energy industry as well. So, but logistics obviously also has an interest in this because of some of the easier types of math problems that can be solved, and so there's a lot of opportunity there for existing industries to get involved now, and some of them, it's just more costly for them to wait. It's still to be determined in terms of who's going to still be around when quantum is reliable and accessible and fault tolerant, and we'll see what happens. The world might look very different.
Thank you. So maybe, Daniel, I'll take a comment on the same question, but I'll also add one more thing. So not just on the industries, but every industry also sees that there are high performance computing centers, which are there, which are powering most of the computation that's happening right now. So combining it with these industries and high performance computing, which caters to these industries, how will the future look like now? So how do the industries prepare is the first question, and how does this high performance computing and the quantum computing, how will they coexist, or what is your vision, or what's your forecast on this?
Yeah, maybe just to follow up on, I think, Rima's comment. fully agreed. I think it's a good time to start taking action now. And I think the biggest piece is probably education, right? Especially quantum is so complicated, right? There's this massive gap between like a physics paper, right, and kind of a hiring or a manager who has to make decision in a company, right? It's not as very straightforward to understand it and to make decisions on like, should we use this technology as an R&D tool, right, to do drug discovery, for example. So I think it's important to right now look for maybe like build small teams of people that understand quantum, understand first of all what's your business doing, right? What are the computational problems, and can talk on the same level of like people like you, right, who like work with quantum computing companies and try to sell quantum computers. That I think is the biggest. That's the thing. If I would be running a company, I would do that, especially if you have the resources and see this kind of as a part of R&D essentially. To your second question on this, what does the kind of compute infrastructure look like? I mean, if you look, for example, of some of the biggest companies in quantum, right? So like IonQ went public, they've published their revenue model. Essentially, they see it as kind of as a part of AWS, right, or whatever, Azure, whatever you want to say. Essentially, where you have as an end user, right, as someone who is basically you run a job on a HPC. You select, I don't know, I want this many CPU cores, this many GPU cores, and I want, I don't know, 5 quantum cores or something like this, right? I think this is the dream, I think, that everyone is after. I'm not quite sure. I mean, obviously it makes sense, right, from economics, from kind of engagement model. But especially in industry, right, especially sensitive industries like finance, pharma, chemical industry, IP kind of leakage is a big issue, right? So, and I know that many companies in that space are not super plugged in on the cloud completely, right? Pretty much everyone does cloud stuff, but a lot of companies also have HPC clusters on site that are run by their kind of own compute teams where they do stuff. And I think something like this I can see also for quantum, right? Especially early machines. You probably need much more maintenance, right? So you can't put it in a rack at AWS, right? You need to have actually people, I don't know, fill in like the helium every once in a while, right? So I can see that something that's at least initially a much more close engagement between giving you a piece of compute architecture rather than like I don't know, you just select another node in a job that you submit somewhere, right? Completely anonymously. So yeah.
Okay. So at least some of the, again, examples, just building on this compute infrastructure and also the industries that I see, it is from my team and also what I follow, includes like the NMR imaging is one way there is a potential where we can crack it. The second one is storm prediction and then climate prediction. Like with all the data that we have from the space, how can the data be computed faster to with more accuracy predict all the climate crisis that we face as a humankind now? The third one, which I heard and read, is something around real-time DNA and how that can be processed to predict and prevent a lot of diseases. The one other one is on route optimization. Surprisingly, although the Google Maps or any other maps that you use work, but then there is still a lot that can be done to make our travel efficient. So there are fascinating problems, like real use cases that I do hear from industry partners and from our teams, which people are working on across different organizations, which I find it very, very inspiring because this is a real tangible problem in energy on the battery optimization. Electric cars is a boom. Yes, everyone needs to adopt it. But what if the batteries can be optimized and can be the new chemical, new material can be discovered, which can make it efficient? And all of these are the promises which I am told that the supercomputing centers or HPC centers cannot solve right now. And the compute infrastructure of the future will be a hybrid where a supercomputer will exist and a quantum computer will exist because a quantum computer cannot solve all the problem. It is like a hammer. So if you have a screw in front of you, it cannot be used to screwdriver like as a screwdriver. So you can only use it for certain purposes. Sorry, you were saying something.
No, I was just I 100% agree. And I think the last point I just want to make is it also, I think you mentioned this already, this kind of more application specific development, right? I think it's going to be very important, right? So we, for example, invest in a company called Seek. It's also one of their main things is being super customer focused, right? Don't even, obviously fully fault tolerant universal is the goal, right? But go to market has to be, I think, over dedicated customer engagement. I think it has to be personal, it has to be focused on exactly what you said, right? Maybe you need a very different quantum computer to do finance optimization versus, yeah, any of the bio stuff, right? So I think that is going to be very critical.
And I was
So
just
with
going to say,
all
I
this
think
good,
I was just going to say,
Yeah.
developing use cases is really key here. It's figuring out, you know, what makes sense given where the technology is or where we think it's going to be, and then playing around with the algorithms and confirming whether they even work, right? Like that's, but developing the use cases is something that industry is working on and we need to continue working on.
One of the
to
use
build on. So
cases,
all the,
yeah,
Mansour, I'll
one of
come to you. I'll ask you a question. I do have a question for
the,
you, and I want to also
Go
add
ahead.
that if all of these are good things, please, you can also respond to that with this question. Additional question is, but what are the frustrations? Like we are talking all the positives or the hope, but why are we not able to move fast enough? So you see the industry from different, like from the talent that's coming out and from the problems that are working on. So why are we not able to make all of this faster?
I mean, one of the problem is maybe what I'm saying is a bit like paradoxical. I'm saying maybe one of the things we want to get result too quickly. We are too impatient, and because, as I said, maybe sorting out this optimization with quantum computing maybe take 4 or 5 years, but it will be done in a very most fundamental, better way. But maybe for a industry now, they want solution right now. So they cannot wait. They may see it as a gamble or something. So this is one of the problem. Whereas if there is more insight, more vision, maybe we get there much sooner than we think. Like, because back to Rima's comment, this learning curve is not usually is not linear, or progression in industry is not linear. We maybe for a while we are stagnant, but then all of a sudden there is explosion of new advances in quantum computing. One point I wanted to say about use cases was the encryption. I don't know if anyone mentioned, which will help a lot in, because one of the problems with using cloud services with healthcare service is anonymization, which is very important, especially in Europe, it's extremely strict. And so if we can use quantum computing capability in encryption, it can actually will opens up a new new door for new advances in medicine and in larger scale analysis without being worried about the identification of the patients, and or in any sensitive matters like I don't know, judiciary, wherever they want to, security services, or yeah, I was going to say something but I forgot. Sorry. Yeah, another.
Sorry, once it comes back, then we'll give you the chance to again comment
Yes.
on that.
Thank
But then, thank you. So let's steer from this. So let's steer away from, yes, the quantum technologies and where we are, and let's look at how we can maybe globally work with and what are the countries doing. And as I start asking that question, I also see a comment that yes, the business value will take another 10 years. And this is also, I repeat what Mansour just said. I think we as a group, as humankind, should not be impatient with this technology. Quantum computing is not incremental. It's a disruptive, different approach towards solving problem. And we should give it its time. Just because there's money being pumped in or media attention that's coming in, we should not assume or we should not expect results sooner. So 10 years could be, in my opinion, an optimistic guess. So 8 to 10 years could be maybe the optimistic expectation. So there is still time for quantum to solve all the problems or universal problems. But going back to the question, So now we are getting into the last 5 to 10 minutes, and let's look at the world from a macro picture. It is the climate crisis is global, affects each one of us, each and every country, and every nation has a role to play. And technologies like quantum technologies have a potential or a promise that they can address these problems. So, my question to maybe starting with Rima, and then maybe from the startups world, then I'll also ask this question to Daniel. But then, Rima, first, do you see enough international collaboration and also public policy which allows for this cross-border international research and collaboration? Do you see that happening, or are we getting into a world where it's becoming protective, specific to these technologies?
I'm going to have to be a little careful here
Okay.
because this is one of those topics where I should not speak for the department. And so I'm going to speak as just, a quantum enthusiast. And in those terms, what I'm comfortable saying is I think we are siloed. The governments are working sort of independently. And I mean, there's a lot of concern and competition. And I mean, we see that even amongst industry. I mean, I think some of the barriers are coming down, but nevertheless, a lot of it, we don't know what we don't know. And so I think everyone's trying to be careful. So that's my answer to, which wasn't really an answer on the topic.
No, I think it is. See, this is a question that was again, the audience is tough, and also this is one of the topics which is less spoken, right? So what you said is the way I see it is, although the public policy and then in terms of the regulations at this point, they are still learning what is the potential of quantum and what are the risks. So they are taking it cautiously as a step. But I also see from the world of scientific community, there the collaborations are happening, research, cross-border, best practice learnings, and so on are being shared. Research papers are commented, reviewed constantly. So there is a way that one of the communities has found it, and also QTAC as the initiative that Daniel was alluding to, where industries are coming together to work on it, which are again global in nature. So I think at the lower level, I do see that there are a lot of those cross-border collaborations which are already happening in a different way. But I agree that from a top-down level, maybe it is more siloed, where maybe for many reasons where the promise of quantum is so big that no country wants to lose the first movers advantage. So maybe once it's cracked, maybe there will be more collaboration is my hope at least. But maybe putting the same question back to Daniel, also on the comment on cross-border, because you don't have a like say public policy hat on you. So do you see international collaboration happening? And also, what do you see from the startups world?
Yeah, it's a good, it's definitely an interesting discussion. I think you're fully right. Like academics don't care, right? They don't see kind of states boundaries, which I love, right? I think on a politics level, I think the issue is that everyone sees quantum as a small brother of or sister of semiconductor, right? And semiconductor is super politicized right now, right? I don't know if anyone watched the State of the Union yesterday, right? Pat Gelsinger got a standing ovation, right, for building a 10 billion fab in Ohio, right? From both sides of the aisle, right? So it is very political, and I think quantum will be in the same kind of groove or whatever you want to call it, simply because I think on a kind of that level is much too hard to distinguish between those two. And obviously, I think Mansour mentioned kind of encryption, right? Anything that has a massive impact on national security, right? Doesn't matter which country this is. I think it's not going to get better. Is my hunch. From the startup side, I would say I definitely see a lot of startups that have kind of places in the US, in Europe, some even in Asia. A big part of that is hiring as well, right? Because it's already insanely hard to hire good people in this field. So kind of if you have two kind of headquarters or two branches, at least that gives you a little bit diversity on that axis. But I don't foresee, I'm not super optimistic on this. I don't think we're going to see this go into a super kind of friendly future. Everyone's holding hands and sharing grants across country lines. But happy to be proven wrong. We'd obviously love to see more international collaboration, especially companies that are international. A lot of the large conglomerates are all international, right? So every big industry player, it doesn't matter, finance, pharma, they're all everywhere, right? So I hope I'm wrong.
Thank you. So, if to the audience who's listening in, if you have any questions, specific questions that you would want to ask the speakers, then please leave it on chat and I'll raise it. But thanks, Daniel. I hope that you are proven wrong and we increase the collaboration and we see a lot more cross-border initiatives. Let me take one question. Maybe it's the quantum poker, right? So maybe if I had to ask you, put you on a spot and say, what's your prediction? When will we see quantum computing useful, like really solving problems? And so what's your estimate? By how many years can we see quantum computers solving real problems? Who wants to go first?
It's difficult to predict anything. Sorry, we were supposed to answer, or someone else was supposed to answer.
No, you can, please.
Okay.
It was an open
Because I
question where
saw-
I would want everyone to answer.
Okay. I mean, as I said, there are early steps have been taken to use quantum computing. It's not that we haven't, like, there is no progress. Actually, the more I get to know the field, I realize there are lots going on. It's not that. But again, this is also a bit subjective matter. What is the full benefit? I mean, because maybe the way we are thinking about benefits, like a bit like goes back to the way we are perceive the world. I mean, so obviously, I think maybe if we say the increasing the number of applications or use cases for quantum computing as a measure of like success or like being widespread, I think it grows. I mean, I'm a bit more maybe optimistic, maybe 5-6 years would be something that we will see at least meaningful progress, probably, I think. But again, yes. I also use this opportunity to say that we talked about industry, about clouds, and one of the obstacles I think in the future we have to see is the communication between CPU and QPU co-location. I think some of the things that IQM is doing, like using co-location, this is one of the important factors. Like one of the obstacles in my own personal experience was that this overhead of communication. I had a similar paper in SIMD, which was actually we used a single instruction, multiple data for parallelization of the high performance computing, parallelization of the keep sampling, and actually we managed to increase the MKL libraries 5 times more the speed. And so the same thing, like for us to use in quantum computing, this co-location and communication between CPU and QPU is one of the important aspects that we should look at. Yeah.
Perfect.
Yeah,
Thank you.
so
If I was an auctioneer, I would say 5 or 6 years was the first answer here. So who's going next?
Yeah, so we do have NSF's prediction. So I don't know if you guys saw this PDF. So NSF is the very first funder of quantum computing ever in the early 80s. They've been doing it ever since, and they say practical quantum computer in 2023. IBM says a similar thing. The CEO says could have a practical quantum computer by the end of 2023. And a lot of these technologies are stage gated, like figure like, shareholders, like they have to limit their progress as they go through all this. So when I hear these two, I heard William Hurley, or Worley, as many as you know him, from Strangeworks say the same thing. He says definitely 2023. open the floodgates. Here we go.
That's optimistic. So we have an outside bidder with 2 years timeline, but I'll still thanks Kevin for sharing this. Maybe
Well, a lot
I'll
of it
go
depends
back
on
to
your
yeah.
Yeah, a lot of it
So
depends
Kev,
on your definition of practical quantum computer. So, what exactly is that? So, is that a laptop or is that a fully functional scientific workstation? And somebody brought up CPU, GPU, QPU. Is it a hybrid? Is it something like Amazon Cloud that's, widely accessible? So, there's Google that said it too, as far as 2029 for useful quantum computer, and then 2025 Honeywell said a powerful quantum computer. So I'm sticking with NSF. They're the first to fund it, and I think we'll see big things next year.
an analyst, good analyst, very reputed in the quantum space, once told me when I was presenting few slides in 5 to 10 years as our timeline where we will see universal quantum computer, like first solving quantum advantage and then universal quantum computers. He said, Raghu, every time I've seen this slide with any company, it has always been in the next 5 years, but the goalpost has been moving. So I'll be very happy in this case to be proven wrong with 2023, but I think it is overly ambitious. But let's see, let's wait and watch, and we will have many more these round tables where we can still continue the discussion. I'll still give the closing words to Rima and Daniel. So, what are your timelines for quantum advantage to be delivered?
Still on mute, Rima.
Did that again. My
Quick
apologies.
30 seconds.
I think it's very important to evaluate what do we mean by a practical computer, right? A practical quantum computer. What we're essentially saying is, are we asking when will we have quantum advantage, or are we saying when will it just give us the right answer? When will it work? When will we know that it gave us the right answer? And I think that timeline is pretty short, right? I think some folks are able. We've got quantum annealers that can demonstrate that, right? If we ask questions that are simple enough that we can test empirically. But in terms of, if we're talking about a quantum computer that can answer very difficult questions, where right now we anticipate we would need 1 million logical qubits, that's further out. I'll stick to the 5-year goalpost on that one.
Fantastic. So, Daniel, your closing thoughts on this. So,
Look. I mean, I think we already have a lot of good answers. I think the range sounds right to me, and it's been 4 years since I've last been in the lab and messed with the laser myself. So I'm just gonna. I think we're good with the range. So I'll stick with that.
all right. So, thank you all for a fantastic roundtable. And here, the thing, it's an important topic. Climate crisis is for real, and it's not something that we can avoid. We need to find solutions, and quantum definitely holds, as a technology, the promise that it will be able to address most of the problems. But thank you for sharing your candid thought. In some cases, not so comfortable questions, but the answers definitely help. So thank you for that. And hopefully the audience here would have enjoyed the session, learned something, and hopefully would have also been motivated to pursue quantum careers. Because one of the biggest challenges that quantum industry is facing right now is lack of talent. So if you find a good person who's wants to pursue a career and if they are interested in technology, then quantum is the space to be. So with that, I'll hand it back to Maëva. So thank you all for joining this panel.
Raghu, Rima, Daniel, Mansour, just really a million thanks for this great session. Thank you so much for a strong final.